Hey, so you made it to the bitter end of Chicago Roboto 2022. So thank you very much. I'm really happy to be here, and what I love about this conference is it's not just about Android; it's about the city of Chicago as well. And I think that gives the conference a really unique personality. And I have watched YouTube videos of the previous conference talks, and I've noticed some of them mention such Chicago landmarks as the Cloud Gate and the Sears Tower. Today I'd like to mention the University of Chicago. So the University of Chicago is one of the crown jewels of the universities of the world, and it counts among its alumni great scholars and statesmen and artists. And in order to honor the University of Chicago, the title of this presentation and the sections of the presentation are going to allude to great American books of the 20th century. So the first part is called a metaprogramming feast, and that's when we're going to talk about what metaprogramming is and why you need it. Next part is a feel out of Stubs, and that's when we're going to explain how KSP is going to help you achieve your metaprogramming goals. Third part is called the Old Man and the IDE, and that's when we're going to try and actually write a very simple annotation processor in the IDE, and that's to inspire you, so you think, okay, well, that doesn't look so hard, he can do it, so I can probably do it. And then last one is called the Great KSP, and that's when we talk about like how to max out your annotation processor and some of the more advanced topics, so that when you design your annotation processor, you're having performance in mind, and you're not going to have to backtrack and rework things. So let's get started. All right, there is a GitHub link. We'll of course post the slides at the end. I would say, don't follow along unless you're one of the people who absolutely must do something in the IDE while the presentation is happening. I think you'll still derive benefit just from passively watching and listening. Right. So onto the first part. So this is a little bit of a reach, I must confess, but the first part is called a metaprogramming feast. And that's named after Ernest Hemingway's biographical work, A Movable Feast, which is about his time in Paris. So what is metaprogramming? Well, very simply, metaprogramming is programming about programs. So more formally, it's programs that take as their input other programs. Most common example that we're probably all familiar with is dependency injection. So for a dependency injection framework, you'd have as its inputs your program, in particular the @inject annotated constructors. And then the dependency injection framework would take that and produce its own programs, which would be factory classes, helper classes, and so on. So if you've ever manually instantiated an object graph in a test, you'll understand the heavy lifting that a dependency injection framework does for you. So you can see there, I've taken the home view model from the Jetcaster Jetpack Compose sample. I think it's a really great project. I've just manually instantiated the view model for a test, and you can see there's a whole lot of constructors calling other constructors, and it becomes a little bit overwhelming. So thank goodness we don't have to do that in our production code. We just have our dependencies, and we annotate the constructors with @inject, and then magically we get all these factories and so on, and we can just request injection and not have to worry about invoking constructors from other constructors and so on. It's not just dependency injection where you get this amazing heavy lifting from metaprogramming. So we've had so many great talks about Jetpack Compose, and of course Jetpack Compose is declarative UI, but years and years ago we were able to achieve declarative UI in Android via Epoxy, which is a metaprogramming framework. And of course, probably people here have used Glide, which is for image loading. And then there's Room, which helps you to leverage the SQLite database so that you can have offline mode and you can build an app that's really takes advantage of the mobile device that might not always have access to the internet. And if you've used any of the great feats of engineering in Android, like the Airbnb app, then there's no doubt that there's metaprogramming in there performing a lot of heavy lifting. Now, for metaprogramming, there's two roads you might take. So you can accomplish it via reflection at runtime, or you can use code generation at build time. Now, we're all concerned about developer experience and local build time, so you might think, okay, well, let's just use reflection. So for Android, it's not such a great fit. And one of the reasons is, as Android developers, we've got no choice but to minify and obfuscate our apps. And reflection and minification are kind of like the sharks and the jets in West Side Story. They're the antagonists. So reflection relies on the fully qualified name of the class, all the members being there just as they're declared, all the metadata being present. And minification, obfuscation are desperately trying to strip away that information. So there's an internal contradiction with using reflection in Android. Not only that, if you do end up using reflection, you might have to add Kotlin.reflect to your APK, and it's not a trivial dependency to add. And the last reason you might want to avoid reflection is if you have a reflection-based metaprogramming solution and something goes wrong, you're only going to find out at runtime. And that might be okay in an Android app where we've just got a few screens and you can exercise every code path in each release. But for a large app with a big navigation graph, it's not good enough. You need to find out sooner, and especially in the context where once something's gone to the Play Store, it can't be put back in, it can't be retrieved. It's difficult to revert that mistake. Almost like a bullet being fired from a gun can't be just plucked out of the air and put back inside of the barrel. So wouldn't it be wonderful if we could have both? If we could have this this build fast behavior like we'd get from reflection, and then also the fail fast that we know we can get from code generation. And this next part, we're going to explain how we might achieve that with KSP. So of course, Farewell to Stubs is an allusion to Ernest Hemingway's famous novel, A Farewell to Arms. So build fast, fail fast. KSP, or Kotlin Symbol Processing, was announced at Google I/O in 2021, but it's been around a bit before then. And it replaces legacy annotation processes that use the javax.lang.model API. So this really old idiomatic for Java API, and that run on in Kotlin projects using kapt. So kapt is in maintenance mode, as you can see there in the little red warning. Now, in case you're thinking, stop trying to make KSP happen, it's not going to happen. KSP is happening. So there's already a lot of annotation processes that have migrated to KSP, or have issue trackers with a lot of votes for migrating to KSP. Now, in case you're thinking, okay, well, then it's just a matter of swapping the old dependency version, the old kapt version for the new KSP version, and then I'll achieve these wonderfully fast builds. It's not quite that simple. I really like this tweet from Zach Swears, and it tells us what we should do and why. So what we should be aiming for is to completely get rid of kapt and its attendant Gradle tasks. So that means you should be aiming for an Android app that doesn't use kapt at all. And if that's not possible, for now, you can start building just one module of your app that doesn't have the kapt tasks in it. Now, that makes a big difference for which dependency choices you use now. So, for example, if you're thinking about using data binding in a new module in a new app, then please don't, because data binding will never obtain a KSP version, and you're always going to be stuck on the kapt version with its old builds. So just be careful with that one. Now, why is kapt so slow? Why is kapt such a problem? Again, referring to this tweet, we get a little bit of a hint about it here, and it's to do with the stubs generation. So hence the title of the talk, which is a farewell to stubs. Now, to find out about these mysterious stubs, I took the Google Sunflower app from a few years ago and built that. And it uses the kapt version of Room, so the legacy version of Room. And if you build that, you get a folder build/temp/kapt3/stubs. And if you have a production class that looks like this, so you can see all those nice annotations that allow Room to perform this heavy lifting for us. In that stubs directory, you're going to get this Java version of the class. So kapt has taken your Kotlin class and written a Java version. And then if you see that set garden planting ID method there, you can see there's an empty method body, just like a stubbed out version of a class that you'd use as a test double. So hence the name stubs. Now, if we think about this in terms of the Gradle tasks, the first task we'd run if we were building a module that uses kapt would be kapt generate stubs debug Kotlin. And this is a task for making those stubs that you saw on the previous slide, that stubbed out Java version of your class. And we've got the little turtle emoji there because that stubs generation is extremely slow. So the reason it can take up to 30% of the time spent in your annotation processor. And the reason for it being slow is because of symbol resolution, and we'll go into that, what that is later. Why do we need those stubs? Well, stubs are needed to run apt. So apt is the Java annotation processing tool, and it can't understand Kotlin. It can only understand Java, hence the need to make those Java stubs. Now, at that point, you might have some Kotlin sources, you might have some Java sources. Dealing with the Kotlin sources first, they'll be compiled with Kotlin C in a task called compile debug Kotlin. And then finally, if you have Java classes, or Java sources, sorry, they will be compiled together with those, with the result of the Kotlin C in a step called compile debug Java with Java C. So you can see 4 steps, 4 tasks there, and one of them is notoriously slow. Now, for KSP, it's much more succinct. You have only 3 stages in the pipeline, and you have this task KSP debug Kotlin. Now, KSP debug Kotlin still does symbol resolution, but it's very judicious and very smart about the way it does it. It's not wasteful like the previous stubs generation task we saw with kapt. So what's the symbol resolution we keep hearing about, and why is it so slow? Well, I took actually some of Mohit's slides, hope you don't mind, and if you think of a compiler pipeline, it's going to take the code and it's going to pass that into a tree-like structure. And the stage of the tree-like structure, the abstract syntax tree, you might think of it as just name only. So you'll know that a function has a certain name, you know that it is a function, but you won't understand the return type. You won't understand how that return type relates to other types, like its super type and so on. To go from the realm of mere name into meaning, you have to perform symbol resolution, and that's what's expensive to do, and that's why the kapt pipeline is wasteful. just continuing with the compiler pipeline while they're there. After resolution, you'd go into generating an intermediate representation, and finally some output like JV and bytecode. So yeah, that's our symbol resolution. I think we've explained why kapt is slow and why KSP can help us get faster. Now let's see if we can build something in the IDE. So switching to Android Studio here. Now I've got a very simple toy project, and it has just three modules here: an Android app module, and then a processor module for building our KSP annotation processor, and then finally an annotation module where we're just going to have the annotation that we're interested in. So I'll open that up in the project view just so it's easier to visualize. Yeah, so Android app, annotation module, processor module. We'll start by looking at the annotation. So declared this annotation called IntSummable, and we'll see how we're going to use it later, but this is just for illustration. So when you're building a toy project, you always run into this problem that, okay, the toy project seems really contrived, but if you were to make like a fully fledged annotation process that was really, really useful, it would be beyond the scope of putting it in a presentation. So anyway, we have this annotation, we've called it IntSummable. It targets a class, and we only need it retained in the source. We don't need to retain it in the binary for consumption with something like ProGuard, and we don't need it. We certainly don't need it at runtime. So that's our annotation. Now we've got this processor module here where we're going to build the annotation processor. And I'll just talk about the dependencies there first of all. So let me look at this. So of course we're depending on, I'll just close that, sorry, clean up some of the noise. So we're depending on the symbol processing API because we're actually building a symbol processor. We're going to use Kotlin Poet for generating some Kotlin code because it has this nice fluent syntax for generating Kotlin code. You don't have to use Kotlin Poet, but it's nice to use. We're going to use this auto service dependency from Zach Swears, which is for helping with service discovery, and we'll talk about that a little bit later. And then finally, we're going to talk about we use this Kotlin compile testing dependency, which is a really nice way to test anytime you're doing something with the Kotlin compiler, and that's been used to test legacy annotation processes as well. So if I go back to our project view, and we're going to start by writing a test just to specify what we want. I'm not advocating for test-driven development or always writing tests first, but we're going to do that here. I'll just talk about the skeleton of the test here. So we have this JUnit rule for creating a temporary folder to store the results of the temporary results of compilation. And we've just got a few helper functions. Hopefully we haven't gone too crazy with extract function. So this one's called prepare compilation. Every time we compile something for this Kotlin compile testing library, we have to specify a whole lot of parameters, and we're doing that here. And then we've just got assert source equals, which just gives us, it's just like assert equals, but it tidies things up a bit. It gives us a bit of syntax highlighting. And then we've got this function to just reach into the temporary directory and pull out the generated files that we want. So just a few helper functions there. Now we'll start writing the test. So we'll use that one. So we need a source, which is going to be input. What's it? Source file, Kotlin. Going to be original and call it foo. And then what's the contents? So we're going to have a data class with some integers and just a string to mix it up, and maybe an extension property as well, just to mix things up. And we're going to annotate that with int summable annotation. And of course, we have to import that. Okay. So that's our source. Now we have to compile that. So, well, we have to prepare the compilation for that. So we're going to prepare the compilation. Then we want to use assert source equals have a function. What kind of output are we expecting? Well, okay, it's called int summable. You can probably guess. We just want to go through that data class and find the int properties. So the int member properties, we don't care about the extension property, and it's just going to write an extension function that sums those. So all we want is something like public fun sum equals x plus y. So that's the output we're expecting, and we expect it to appear in a file called foo.ext.kt. Okay, so that's the kind of processor we're going to attempt to build right now. So, okay. I'm not going to run this test because I'm very scared that it's going to gobble up all the CPU and it's going to disrupt the stream. So, but spoiler alert, it will fail because of this line here. So when I'm preparing Kotlin compilation, and I'm using KSP, I would need to supply a list of symbol processor providers. So that gives us a clue about what to do next. So we'll do that now. Obviously, we have to write a symbol processor provider. So if I go to my project view, and we need a main source set. And we need a package. I'll put it the same package as a test. Oh, yeah. Okay, now we need to write our symbol processor provider. So we'll call it int summable processor provider. Okay, and we'll close that just to get rid of some of the distracting stuff on the screen. Okay, so now we're going to start writing the KSP annotation processor. So we said we needed a symbol processor provider. So we obviously need to implement the interface here. Now, okay, the IDE is complaining about something. What's it complaining about? So we haven't fulfilled the contract there. So let's see if we can just get the IDE to do that for us, implement all the members we need to implement in order to fulfill the contract. And luckily there's only one, so it's a nice demonstration of how having a small API service can help you to work out how to do things. All right, so we get a function called create, and in there we've been given a handle on a parameter of type symbol processor environment, and we have to output some kind of symbol processor. Let's just have a look at what goodies we get inside the environment, just to give us an idea of what to do next. So if I type in environment dot, then you can see we get a code generator, we get a logger, and Kotlin version, and some options. Those first two look kind of useful. Let's write a symbol processor now, because we can't start creating a symbol processor if we don't have one. So summable processor, and we need to implement symbol processor. Okay, and let's let's think about what things we need to get from here into here. So when we looked at the goodies, we saw that code generator looked useful and the logger looked useful. So let's put those in. Code generator. Okay, and then now we can actually finish our symbol processor provider. So we're just going to make the symbol processor, and we're going to unpack the environment just like that. Okay. Right, now the IDE is still complaining. What's it complaining about? Okay, so we haven't fulfilled the contract again. We need to implement this function called process. So let's just do that. Okay, so now we have this function called process. We get a parameter called resolver, which we can use to inspect the code. And we have a return type, which is a list of KS annotated. So what's that talking about? Well, if I just look at the documentation there, it's a list of deferred symbols. So this is talking about when you want to play really nicely with other annotation processes, or where you're doing your own kind of multi-round annotation processing, where you're emitting some code in the first round, and then you want the second round of annotation processing to pick that up and build on it. Now we're just going to ignore that for now and return an empty list to make things simple for us. So just to fulfill the function contract there, but if you do want to read about how multi-round works, then there's a really nice explanation in the KSP documentation. Okay, so breakdown of what we're trying to do is get all of the classes with int.summable annotation, and then get the int member properties, and then write an extension function to sum them. So we want to accomplish this first step. Now we don't have much to work with apart from the resolver, so let's just try using the resolver and type in dot and see what we can get. So there's quite a few functions there, but I'm looking for a way to get annotations. So if I type in annotation, then this function pops out, get symbols with annotation. So that sounds very promising, and I just have to specify the name of my annotation. It was int.summable, wasn't it? Okay, now the return type is a sequence of KS annotated. So we're going to just map those. Right. I'll just put that on the next line if you don't mind. Okay. So, right, now we're able to iterate on all the classes in our module that have that int.summable annotation. Now, if I type in KS annotated and look at the autocomplete there, there's not much information. It's not really useful. I can get the annotations, I can get the location and the parent, but there's nothing like no way for me to get the properties or anything like that. So if you remember our annotation, we said we can only target classes, we can't target anything else. So we can use that to our advantage here. We can say, we can cast it as a KS class declaration because we know that that annotation can only target classes. So we'll do KS annotated as KS class declaration, or throw int.summable can only target classes. All right. So now we have KS class declaration. Now, if I look at the autocomplete there, there's a lot more useful things. So remember, we have to get the properties typed as int that are member properties. So we're ignoring extension properties. Now, if I type in properties, there's two functions for me to choose from. There's get all properties, which if you look at the, it's not showing there, but if you look at the documentation, that's talking about properties from the superclass as well as properties explicitly declared. And then declared properties is the opposite of that. So just what's declared in the class. So I'm going to use get all properties, and I'm going to just put them in a val there for to make things easier. Now I have to filter out here. So I have to filter out extension properties. How would I do that? Well, if I do filter and then it, so it here is a KS property declaration. Okay, but you can see if I type an extension, I get this property called extension receiver, and the way of saying member property is extension receiver equals null. So nice and easy. And then, of course, I need type as an integer. So how do I do that? Well, okay, if we look at the KS property declaration, we can see there's type available for us to inspect. Now, if I look at what type gives me, again, it doesn't give me a whole lot. It just gives me element, location, things like that. And that's representative of what we talked about in the slides earlier, where at the level of the abstract syntax tree, you just have name only, and then to go from that into the realm of meaning, you have to actually resolve and perform symbol resolution. And that's what we're going to do here. So we're going to actually resolve the type there. And you can see after we've done that, we immediately get much more information. We can see whether the type is nullable. We can see if it's assignable from this and that type. So all I want is, I want to see that the type is int. So how do I get int and other common types? Those are actually inside the resolver. You get this, this property called built-ins, and then it has all the types you get out of the box in Kotlin. So we're going to do that. Now, it's a sequence. I'm going to materialize it as a list just to make our lives a bit easier for the next step. Now, I need something to return from the map. So I'm just going to declare like a really simple data class to store the results from that map. So I can't think of a better name than just data for that, unfortunately. So we're going to store the class declaration and the props, the properties. So that properties is a list of KS property declaration. Okay. And then we've got a nice type to store the results of the map. Okay, great. So we've done the first part, which is get all the classes with int summable. So, and we've also done get the int member properties. Now we have to, actually there's an edge case. What if there's no int properties? So in that case, we don't want to output any code, right? So then we just do filter not it props is empty. I suppose we could be super smart and try and do map not null and try and avoid the extra iteration, but I don't think it's important at this stage. Okay, so now we're going to actually write the code. Writing the code is like a side effect, so we'll use for each. And we won't use the explicit, we won't use the implicit lambda parameter there. Now, how do we write a file using Kotlin Poet? We get this, you write a file spec, and okay, package name is going to be, it's going to be in the same package by convention as the as the target of the symbol annotation. So we'll just get that data KS class decoration package name. Now you can see package name has a type of KS name, so that's easy to resolve to a string. We just do add string, and then file name. Okay, the file name, we said it was just going to be the name of the class plus ext. So it's going to be data, KS class decoration, simple name, add string, plus ext. Okay, so that's our file spec builder. What are we going to have inside that file? Well, we basically want a function to summarize ints. So to sum the ints, sorry. So we're going to do a fun spec.builder. Now, what's the name of our function? Name is sum. What's the return type? Well, it's obviously integer. Now, what's the receiver? Now, this is a bit more tricky. We want the receiver to be the target of the int summable annotation. Now, for receiver, we've got a few different options. We can supply a K class, a type, which is from java.reflect, or a type name, which is Kotlin Poet's way of dealing with types. So we're going to use that top one, type name. So what we have to do here is somehow get that KS class declaration into a type name. So KS class declaration. And we can actually resolve that as a type. Right? What's this type arguments here? Well, when we declare a class, we can obviously have type parameters like that. Now, that list there, when you do as type, is for whether you want to actually resolve those type parameters with type arguments. So we don't here, we're not going to bother with binding any types there. So we're just going to do empty list. And then, okay, so that gives me a KS type. I have to get from KS type to Kotlin Poet type name, and there's an extension function for that. So I'm just going to use that. Okay, so we've got the most important parts of the function. We've got the return type and we've got the receiver. Now, how do we get the code? So we're going to add returns, return, and we're going to be clever and use join to string. So we have the property declarations and they're in a list. So we can join them to a string with the plus separator like that. And then we have to obviously write a lambda there to say how we're going to use those KS property declarations. Well, we actually just want the simple name. So simple name add string, just like that. And ID is complaining because I haven't actually built the function. Right, so we've got our file spec, we've got our function inside the file spec. Now we have to write that. So how do we go about writing? Well, we get this extension function supplied by Kotlin Poet, which allows interop between KSP and, well, it allows you to use the KSP code generator with Kotlin Poet. So we want write to code generator. And then we have this aggregating equals false or aggregating equals true. We're going to talk about that later because that's probably one of the more confusing things. And just like that, we have our annotation processor. That's going to be enough. So how are we doing for time? I think that's enough about typing the annotation process in the IDE, let's go back to the slides and just cover this aggregating equals false, because that was really important. So that aggregating equals false that you saw there is about incremental processing. So that's making sure that when you write your annotation processor, it's performant. And then if you make a change to the inputs in your module, you're not going to have to rebuild everything from scratch. So we're talking about that Boolean flag that we passed in there when we use the code, when we use write to. So let's try and explain that using a really simple annotation processor. Here's one that takes classes annotated with @interesting, and it's going to output an extension function with the suffix ext, and it's just going to print out fascinating. So we have a.kt in our module. We have a whole lot of other source files. So if you think about inputs in general, the inputs in general are going to be the sources inside your module. Now, when we get aext.kt as an output, we're going to register a.kt as an input, and we're going to represent that using the black arrow there. So we have inputs in general and registered inputs. Now, the question we need to be asking here is, what would happen to aext.kt if we added some new source? So let's say we add b.kt, and it also has the interesting annotation. That's going to generate its own file. It's going to have nothing to do with aext.kt. And it turns out whatever kinds of crazy sources we might add, there's no way we can harm aext.kt as an output. So because aext.kt is protected or isolated from having to change due to some new source outside its registered inputs, it's called an isolating output. Now, the opposite of that is aggregating. So here's another annotation processor. It looks for this @interesting annotation, and it's going to collect all of them into one single output. So this output called fascinating.kt, and it's going to have a class with constructor parameters where the parameters are typed after the input. So if I've got this situation like that, what would happen to fascinating.kt if I added some new source? So of course I could add _.kt, and that would have if that had the @interesting annotation, that would harm that output, fascinating.kt, and it would have to be rebuilt. If it was rebuilt, the inputs would have to be processed again. So because it aggregates or collects potentially new information outside of its registered inputs, it's called an aggregating output. Now, you might think, okay, aggregating is a bit useless then because we always have to look outside the registered inputs. Well, what about this situation? We have A, B, and C as registered inputs, and D and E are just normal classes, normal files that happen to be inputs in general, but not registered inputs. So what would happen if I deleted those? Well, turns out deleting them is safe, because if they're deleted, there's no way we can add potential new information that fascinating.kt as an output would have to aggregate. So that's an optimization that you can get from aggregating outputs. And there's a really nice summary in the KSP documentation. And you can also look at the Gradle documentation, because Gradle annotation processors that run with kapt also have this concept of aggregating and isolating. So we're running short on time. I'm going to skip X processing, but X processing is basically a way for you to rewrite a legacy annotation processor you have that uses kapt, so that it can also use KSP. And it's really interesting to read about. It was treated by Yigat Boya in one of his blogs, so I'd encourage you to read that. But I'm David Rawson. I work for a company in New Zealand called ClearPoint, and I'll put the slides up on Twitter. I'm really happy to be in Chicago, and I hope one day I can reciprocate and host you in my country and in my city. And thank you for listening and hearing about KSP.